Hi, it's me, Carolyn, and it's time for another video. We are going into chapter 7, which now starts looking at continuous situations and how we define probabilities of a continuous situation because we have so many different possibilities. We can't, first of all, do what we did with a discrete and kind of list them. So we have a different approach to those. I'm going to start our share so we can look at our guided notes and kind of walk through those. Oh, there's my cat. I got him to move though, so we should be good. So again, we're in 7.1 and a continuous random variable, first of all, it does cover an interval of values. Now, these intervals could be small, they could be quite large. And so creating these distributions like we did, writing them all down, not possible. So what we have is something called a probability density function or a PDF, different from the PDFs in the computer world. But it is a probability density function. And it's an equation that we're going to use to compute probabilities of continuous variables. And it has to satisfy two properties. These properties are very similar to ones that we saw with the discrete models. First of all, the total area under this curve. So if we graphed it and we looked at all the possibilities this random variable takes on, that total area has to equal 1. This is similar to when we add up all of our probabilities, we get 1 from the discrete model. The height of our graph, so if we graph this again, we have to always be greater than 0. That's going to be similar to probabilities being between 0 and 1. Now, we can, in these situations, be larger than 1, depending on the possibilities for our random variable. We're going to look at a couple different examples, but before we do that, just some other situations. We don't look for the probability of a single value. Like I'm not going to look for the probability that a person's weight is 126 pounds. Because there are so many possibilities, the probability of a single value is so negligible. We call it, it's basically 0. So the value, so think about it, in the continuous world, the probability of a single value is going to be 0. So we're going to be looking for probabilities of an interval, like the person's weight is between 25 and 26 pounds, giving us some little bit of range. And the way we're going to do that is we are going to be finding the areas under that curve. The way this is set up, these probability density functions, that area under the curve of those over that interval will be the probability of that interval happening. So kind of keep that in mind of this correlation, that the probability of X is in some interval is going to be the area under the graph over that interval. Okay. So let's first of all consider our uniform. Now we have to remember what our uniform distribution looks like. And I'm going to just kind of, let's say that this one represents the number of minutes late for class. Okay, and let's say that it can range anywhere from 0 to 30 minutes. Since the area under this curve, uniform, remember, is flat. So the area, this is going to be flat for this area, this region here. Every place else it's 0, so it is above 0. But for this to be a probability distribution, the area under the entire curve has to be 1. So now this is a nice shape, even though my picture is kind of not perfectly perpendicular. It has to equal 1 since it's going to be the rectangle, and an area of a rectangle is length times width, or base times height. My base is 30, so for me to get a height or an area equal to 1, I know that this height has to be 1 over 30. Okay, I'm going to get a couple colors here so we can draw some pictures. All right, in this first one, we want to calculate the probability that the time missed or the time that we're late is somewhere between 5 and 10 minutes. Now, remembering area under area probabilities is the area under the curve for that same region. So I'd be finding the area from 5 to 10. So I'd be looking for this shaded area. Now, again, it is a rectangle. So the area of a rectangle is that base times the height. Our base is 5 units, and our height is 1/30. So if I multiply those together, I get 1/6, which I could write in my decimal form. So again, fractions or decimals are fine. It is repeating 6, so I'll just go to 4 digits and put 0.1667. Okay. So again, probabilities for a continuous situation, areas under that probability density function. So if I'm same problem, same situation, I want to go the probability that x is greater than 27. And so 27 we'll put, I'll kind of draw him here, even though it's a little bit scales off here, we can handle it. And greater than means from here all the way up. But notice we don't get anything because the graph it doesn't exist beyond 30. So we really only have that little chunk. So again, the area of a rectangle is our base. So from 27 to 30, that is 3 units. And our height, which is 1/30, base times height. So we end up getting 1/10, or in decimal form, 0.10. Okay. That's a little bit with the uniform, and I like using the uniform to kind of introduce this idea of areas under curves because it does give us some areas we can actually calculate. Now, the normal curve, which we've seen before, it's also sometimes referred to as the bell curve because of that bell shape. It does have those properties that it is always above the x-axis, so it's always positive. And if I did take the area under the entire curve, we do get 1. The formula for this curve, and it does change as your mean changes or the standard deviation changes, and I'll look at what happens with those changes in just a moment. But the formula for this curve, and by no means will we ever need to use this formula, looks like this. And notice that we have our standard deviation in here in a couple places. Here it turns into the variance. We do have a square root of 2 pi. Crazy that that value is in there. And then we have this e. If you can remember, e is that base on your natural log, so like 2.7 something. And there's our mean. So again, a very complicated formula. However, lucky for us, someone has done all of the mathematical work behind it that we won't have to do all of that. So, but that is just for your reference, for your information, for your curiosity. That's the formula for our curve. Okay. So what happens to this curve if the mean changes? Let's say we have a mean that's equal to 5. Okay. Just some things to kind of note. I'm going to put a number line here. The normal curve, first of all, is centered around that 5. So the highest point on our curve is 5. So kind of draw this. Sometimes my curves look pretty good and sometimes they change. If we keep our standard deviation the same, if I change the mean to, let's say, something larger, so mean equal to 10, what's going to happen is this curve is going to slide over. So we'll have the same curve, but it's going to, hopefully I can draw a exact image of this thing. Oops, I missed. So I'll move my 10 here. There's my 10. Again, the highest point is on that curve. Some other nice pieces of information is that the mean is in the middle, okay? It's also the mode, because mode is the most often occurring. Since it is the highest point in our curve, that means we have more people under there. It is also the median, because median means middle, and our curve is beautifully symmetric. A true normal curve is perfectly symmetric. Another nice fact that we have is that we have these, what we call inflection points. Okay, and an inflection point is where this curve changes from, the best way to illustrate it is from being bowl shape up to bowl shape down, or vice versa. So if you think about a cereal bowl or a ice cream bowl, right here it's kind of bowl shape up, but it switches to bowl shape down, kind of about right in here. And then it does the same thing on this side. It turns out that for our curve, those two places happen to be one standard deviation in each direction. So one standard deviation. So this would have been at 5 plus whatever our standard deviation was. And here would have been 5 minus our standard deviation. Here it would have been 10 plus and 10 minus. So going one standard deviation in either direction gives us those two, what we call inflection points. Okay. Also remind you that the empirical rule does hold for the normal curve. Remember, we talked about that. And the empirical rule says that if we are within one standard deviation away, we get that 68%. So that will come into play again as well. So just kind of keep that in mind. So we still have all of those nice things happening for us. Okay, so now again, if the mean changes, all that happens is the curve moves up and down and is centered wherever that mean happens to be on like a number line. Okay, also notice that the mean, this normal curve goes on forever. Even though my picture doesn't show it, it does come very, very close to that 0 mark very, very quickly. And this picture does a much better job than I could ever draw, but I stole this one off the internet. And what happens if we change the standard deviation? Now, standard deviation, again, measures how spread out the data is, measures spread. So the smaller the standard deviation is, the more tightly compact the data will be. Also, it's going to be moving those inflection points in because you're going to be becoming smaller, so closer together. Remembering that the area under the curve has to remain the same. So think of it as a balloon that has a certain amount of air in it, and you squeeze it together. What's going to happen is that balloon is going to force itself up. So that's why we don't have a restriction on how tall these things can get, because if we have a very small standard deviation, our data is so tightly compact that the air or the people or whatever we're measuring has to go somewhere. So it's got to go up. So that height is changing. So A is going to have a smaller, this one has the smallest standard deviation. I don't know what they are. Does not really matter. Just kind of want you to know what happens to the shape of this curve as that standard deviation changes. If this standard deviation is right here, this is kind of in the middle. So this guy here, that B, would have like a middle range standard deviation. I'll just say mid-range. And this one here that got a little bit flat, it's kind of spreading those out again. So if you stepped on it, it would go out like that way. And so this one is going to have a larger standard deviation. But again, remembering that our area does have to remain at 1. So we're going to be pushing people out, which means our height is going to get a lot smaller too. Okay, so that's kind of what changes when the standard deviation changes, gets smushed in or gets flattened out. And of course, you could do all of those things together. All right. In general, I already kind of said that it is centered around the mean, and it does have those inflection points, 1 standard deviation, both directions. And a lot of times, since every situation is different, you might have a different mean, a different standard deviation. What we found is that we can transfer all of these to what we call a standardized version of itself, one that is going to be centered at 0, that has a standard deviation of 1. And we'll study this quite a bit. And that way, we only had to work and do all the math on 1 curve, and then have to have some sort of little formula for us to be able to take any curve and transform it into this curve. And we've seen that formula already. And we get to that standardized curve by looking at z-scores, which we saw in chapter 3 when we were looking at position. And we will see this again a little bit later in chapter 7, actually in the next section, how we take any normal curve and we can, what I like to call is standardize it and turn it into the standard normal curve. And then we can use all the math that happened, all the studying that happened on the basic standard normal curve to answer whatever question we want to. But that's in future videos. And so I am going to stop my share here now. And in our next video, we will look at the standard normal and learn how to use it. And I'm going to be working with a table. There are different tables out there, so just kind of be aware that if you're looking for tables out on the internet or Googling them or whatever, there are different tables. StatCrunch does do the standard normal and things of that nature, but I still like using the table, especially since a lot of the homework questions, they don't always give you StatCrunch. And having that table available to you, learning how to read a different type of table is also a nice skill to learn. So we will be kind of working through with those tables. And I will see you guys all in the next video.